So chapter 4 is basically applying the rules and the rules that we learned in chapter 3. So application, yes, we are going to see a number of word problems, but usually the derivatives that we see, so I know that there are some really complicated derivatives on the test. The derivatives that we apply here are usually not as difficult, but yes, we have to understand what the word problem is and how to go about it, and that's usually the hard part in this chapter. The first section, I'm hoping will look a little bit familiar from pre-calculus because we did, or you should have addressed what extreme values mean. Okay, we'll review extreme, like maximums and minimums.
Oh,
Got it.
Do not
Okay.
say it like that, Ms. Casey.
Okay. Whenever I say extreme values are your maximums and your minimums. Okay. So first of all, if you ever see the word absolute, well, absolute means that there is only one. It's on a delay or something. Absolute. Let's see. Absolute means one value. Now, it could occur at more than one location. Just an example would be your sine or your cosine curve. The maximum, like if let's say it's a sine curve, right? Here's 1 and here's -1. So you know your graph, so, well, like those are both maximum points. The value is 1, but it occurs at infinitely many places. Does that make sense? But there's only one absolute maximum, there's only one absolute minimum. So first thing we need, oh, and I should probably write this down. Notice it says here domain. Right here on the domain.
Oh, yeah.
When we refer to these absolute maximum and minimums, we're looking on a closed interval. Okay, and that will lead into what we're going to look at on the next page. Sorry,
Oh, now I remember.
okay. So just right here, I just talked about sine and cosine. What is our maximum, our absolute maximum, and our absolute minimum value, and where does it occur? So our maximum is going to be, I didn't label this, but you guys should know. Okay, so our maximum is equal to 1 at x equals what? Where does it reach 1? Pi over 2. And here, just on from negative pi to pi is what I've graphed. So here, our minimum value is equal to -1, and this is at x equals negative pi over 2. Right? Here, on the cosine, we have a maximum value of 1 at x equals 0. But here, we have a minimum equal to -1, but it's at x equals negative pi and pi. So when I ask you just for the minimum or maximum value, I'm referring to a y value. So these, the min, the max value is a y value. Where it occurs is going to be your x value. Does that make sense? Because when we get into optimization, when we want to have like a box and maximize the volume, the maximum volume, that's our y value. That's what we would look at. Okay. All right with that? Okay, so here, this is where I was talking about absolute max and min. Definitely depends on the type of domain that we're working with. Okay, so the first one is on all reals. An absolute max. So imagine here we have x squared. And even though it's not there, we know the arrows are there. It continues. Is there an absolute maximum value?
No.
No. So we're just going to write none.
Oh, so we wouldn't write infinity?
No, so maximum and a minimum value must be a real y value. So infinity is not a real number. Okay, we can't find it on a number line. So we just write none. But this one does have an absolute min. The absolute min is 0.
Equals 0.
Y equals 0.
Yeah.
So remember, these are all,
Yeah.
it's okay. Just, these are going to be our y values. I'm not going to worry about where they occur. You can see it. Now, what happens if we have brackets? So now, it's almost as if I want to take away these arrows, and I'm going to put closed circles. Does that make sense? By putting closed circles, it means I'm including the endpoints. So now my absolute max is 4. And that occurs at 2 locations, at -2 and at 2. But it's still just my absolute max.
But it's only from 0 to 2.
Oh,
Yeah.
whoops. You're right. Let me erase this then. Sorry, guys. So if we're looking at 0 to 2, we're basically ignoring that part. So let me rephrase. So now if we look at from 0 to 2, these are my 2 endpoints. So now my absolute max is 4. My absolute min is 0. What if I have parentheses at the 0? So now instead of a closed circle, we think of this as an open circle. Does that make sense?
What would our min?
Okay, so here's the thing. Here's the problem with the parentheses. Parentheses means we're getting closer and closer and closer to that, but we never actually reach that value. So there's always going to be something closer to it, and then there's always going to be something closer to that, and it's just, but it's never going to reach 0. So if this is a parentheses, if this is open circle, we write none.
What, really?
Really? Oh no, I'm sorry. I keep writing in them. Thank you. Boy, oh boy.
Like, Eli had
I was referring to this point, the minimum.
Eli had brought the maybe like 0 plus.
No, there is no such thing as 0 plus.
Yeah.
So why are we learning calculus?
Why is 0, what's 0 plus? Tell me what 0 plus is. Okay, is it a real number?
0 is a little
Can I actually reach 0 plus?
Or wait.
No.
No, it's not possible.
Not possible. Okay, remember, these have to be real numbers. So if you give me something like a 0 plus, that doesn't mean anything to me in terms of a real number. It has to be 0, or it has to be not 0. And since this doesn't actually reach 0, and there's no value, like, okay, so 0.1, but could I find something closer to it? 0.01, 0.001, 0.0001. So that's your idea of the 0 plus, but there's no actual value that would be a minimum, because I could always find something closer. I know, it's a little confusing, but with the parentheses, it just means it's never going to have that smallest value. The maximum we do, because that's filled in, so that's 4. Now, the last one, what if we were to put open circles at both? So now we have none and none. So I just wrote this one. So this example shows that a function may fail to have a maximum or minimum value. Okay, this cannot happen with a continuous function on a finite closed interval. That's just my little note here. So finite closed interval would be this one. So notice whenever I have a closed domain, or you have brackets around the endpoint, we're going to have an absolute max and an absolute min. But if there's parentheses involved, we're not necessarily going to have that. Yes?
For the last ones, where it's the parentheses, wouldn't the absolute max be 1 point, or wouldn't it be like 3.999?
Okay, so that's similar to what Elijah was asking in that 3.99, 3.999, 3.999. We'll keep going. Do you ever actually reach a number that would?
You can do the truncating thing though.
Okay, so that's why he was suggesting using 0 plus, but 0 plus isn't a number. So what you're describing, Adam, would be 4 minus. But 4 minus isn't an actual number. I understand it describes what it's getting closer. That would be the actual limit. But does it actually have a value? Does it ever reach this number? No.
You
So that's
express
not,
it as a fraction.
it just doesn't exist.
There's always a closer fraction.
There's always a closer fraction, and then there's always something closer to that. Let's look at extreme value theorem. Maybe that will clear up, and then there's a number of examples here. So extreme value theorem, this talks about that last little thing I wrote here and highlighted, a finite closed interval. And we'll abbreviate, so there are a few theorems in calculus that you need to just know right away. As soon as I say extreme value theorem, or we'll abbreviate EVT, you should know what I'm talking about. So one of the ones we've already talked about and you had back in pre-calculus is intermediate value theorem. This is extreme value theorem. And then we'll also have mean value theorem.
Isn't the first one just if the domain is here and here, there's a point always in
Yes,
between?
that's intermediate value theorem.
Yeah, that's not really a theorem. It's like, hey, look.
It's,
If I go from here
remember
to
from
here-
geometry you had some of those theorems that were obvious, but you still had to prove it. Same thing in calculus. We're not going to prove it. That would be something you'd see in an advanced calculus class.
reflections or
But-
whatever?
But doesn't AP stand for advanced plate screw?
Do you want to
I'm not
prove
saying
it?
that-
Do you
I'm
want to
not
prove
saying
it?
that, I'm just asking, like.
Reflected, it's the same number.
Okay, so, oops.
That was so frustrating.
Here's a couple things that you have to basically memorize. Okay, you'll see this on the AP exam. They'll say, can you apply the extreme value theorem? Well, you need to first make sure it's continuous, and you have to make sure you have a closed interval. So think of, that's your hypothesis, because I may ask you, does the hypothesis to the extreme value theorem apply? Is it satisfied? So if you have a continuous function, which we should now remember what that means, right? And it's on a closed interval, so you can't have any holes, you can't have a jump, you can't have a vertical asymptote, okay? Then, oops, f has both a maximum and minimum. So kind of like continuous and closed interval implies that you have a maximum and a minimum. That's basically what that's saying. So you have something continuous on a closed interval, meaning you have filled in endpoints on both sides. It has to have both. Now, sometimes the maximum and minimum value end up being the same thing, like a constant function. But most times they'll be different, okay?
Is there anything other than constant function that has the same thing, maximum and minimum?
Okay, so there are some cases where we saw on the previous page, if it's not, first of all, if it's not a closed interval, then we throw out the extreme value theorem. But you still may have a maximum and minimum value on a non-closed, or a max and not a min, or a min and not a max.
Or both.
I'm just saying, if you have a closed interval, you have to have both. You have to have both. What were you gonna say?
No.
Okay,
Nothing
so
I would
some,
add anything.
so here's some examples. So here we have, here's a maximum, here's a minimum. These are examples whether it's on the interior. And we're imagining here's our endpoints. So sometimes the maximum value is on the interior. It's not one of your endpoints saying for minimum value, right? So here's our max. Here's our min. These endpoints, you may remember the term local max and local minimum.
Uh-huh.
Okay, so we'll also have those, but for right now, just this part is focusing on absolute.
I remember that because of the accent.
Here,
Because I was the first
here's our maximum and here's our minimum. So sometimes it does end up being at the endpoints. Okay. And then maybe we have a maximum, a maximum here and a minimum at one of the endpoints. So you could have both, a combination. And here we have a maximum and here we have a minimum. Okay, so they could, basically what this is just showing, sometimes the maximums are
Isn't that
on the endpoints?
different places?
And sometimes they're in the interior. They're not on the boundary points.
Isn't the big M and the little m already say that? Like big M maximum?
Yeah, big M is the maximum, little m is the minimum. I just was writing out the little
I
abbreviations.
just wanted to check.
Oh, I didn't realize that. That's a good point, huh?
Okay, so the local extremes or the relative, you need to just be familiar with both of those, local or relative. So absolute maximums and absolute minimums apply, they qualify as local, but then you have additional ones. So for example, right here, this is the absolute max. And right here, this is the absolute minimum.
Define local.
Okay, so local means that if you were to take, okay, like for example, right here at C, if you look at the points just to the left and just to the right, and you can kind of, it's almost like zeroing in or zooming in just on this point. Is there a maximum in this zoomed in window? Yes. It might not be the highest point on the graph, but it's still a high point in this region of the graph.
How do you determine where you like, as long as there's like a good change of places, it's a local max, local min, but it could be the absolute.
Right, so what you want to do is you want to kind of restrict where you're looking at to only include
The point.
that particular
The
point. Like we
little
wouldn't
curve.
go from here to here, or we wouldn't go from here to here, because then you would have points over here higher, and you'd have this.
So you just want to take where it, like where it switches kind of directions, and they're always
That's a
local,
good, okay, that's,
or no?
let me explain. That's actually a very good question, because that's something that we'll look at. How do we know if it's a local maximum or a local minimum? It has to do with the graph goes up, and then it goes down. Okay, and that's where we're going to relate the derivative and so on. When it goes up and then it goes back down, that's going to be a maximum. Then a minimum is when we go down and then we go up. So that's a minimum versus the maximum. So if you look here, this went up and then it goes back down, that's a maximum. And then here we're just going down, but it's an endpoint, so that qualifies as a minimum. So you have kind of a combination here of local maximums and minimums, and then you have the absolute. Absolute is like, absolute also qualifies as a local maximum or minimum, but it just has that added piece of being like the highest point on the graph or the lowest. Natalie?
So, a question more would be asked is, would it be something like, between, if the domain is AB, and you're looking between AE, what is the maximum, or the local maximum?
Yeah, you could, well,
Like, how would it, like, what should I?
so
be-
I would give you a domain and I would say, okay, to write down the local maximums and the local minimums, and then identify of those which ones are absolute.
But we would never have a domain where we'd have to go, like, where it exceed our calculators, would we have one that would exceed our calculators?
No. Just looking at how much time we have, because otherwise we're not going to get through.
Well, you gave us 2 days for this.
Yes, I know, but I wanted to get at least through like an example.
We did on the first page.
We went through
2 examples already.
Yay.
Go us.
Okay.
Don't feel bad, Ms. Kasich.
So do we have enough information to start the homework, or?
That,
we not
I
do
I wanted to get through one of these, but
I like that font, it's really big.
So you just like big fonts?
I do like big fonts.
You know, you should just judge back into the fonts.